Hello, and thank you for joining us today for EISA and variable load applications. I'm Dave Grabowski. Today we're going to be looking at how the Energy Independence and Security Act has impacted the use of energy in variable load applications and some of the opportunities there for improving energy savings. With us today are John Malinowski, Senior Product Manager for AC Motors with Baldor Electric, Ted Clayton, Kaman Industrial Technologies Manager of Energy and Power Management Services, and Bruce Benkhart, Director of Industrial Programs with Applied Proactive Technologies.
Thank you, Dave.
So John, let's start with the basics. When we say variable load, what are we really talking about there?
What you're talking about is a centrifugal load like a pump or a fan that changes. It's not a constant torque load like a conveyor. If you had a conveyor and you change the speed of it, the amount of torque required at any speed remains constant. A variable torque load, as you change the speed, the horsepower required for that changes by the cube of the change.
Okay, so relative to the EISA legislation, why is this such a big deal, and why are the two linked together?
Well, the two are linked together because the new Energy Act is requiring more motors that are NEMA premium. And those motors have a capability of being used with drives. They're inverter ready, if you will.
I think part of what I look at when I see this opportunity, you have the motor itself, and that efficiency is now moved up. We'll call it, for all practical purposes, about as high as it's going to get. And then in the application, typically people are controlling flow. It could be liquids in pump systems, it could be air, and oftentimes there's a mechanical device that's doing the actual flow control. So the high efficiency motor is running at fixed speed, always on, and then the process demand is satisfied with this mechanical device. So I'm particularly focused on it because there's a system opportunity. Let's deal with the losses that occur with the mechanical control, and let's deal with the speed of the fan or pump directly in the combination of the motor and the variable speed drive. Mainly because at that point, that's where things really get exciting. The component efficiency, we'll just say maybe it's a 5% benefit. You gang a couple together, you might be swimming in the 10 to 15% end of the spectrum. But dealing with this mechanical flow control and optimizing the entire process, you can be talking 30, maybe as much as 50% energy savings. Mm-hmm. That's where it really all comes together as I work with customers and as we look at the total opportunity.
And of course, manufacturing operations vary widely depending on what it is that you're producing. But Bruce, do you have any sense in terms of how prevalent these opportunities are?
Well, as we've touched on before, a good 70-75% of all the electrical load in most industrial facilities is motor and connected horsepower loads. And of that, a substantial portion, 50-60% of that, are these kinds of potentially variable loads. So there's a great opportunity there. Okay. And we see a good deal of that in our motor audits. We see many of these applications, and we also see these applications not being controlled by variable speed drives. We see them being controlled with throttles and valves, which are simply inefficient and wasting huge amounts of horsepower.
I see. Hey, John, it's surprising these days, but when you start talking about variable speed drives, there's a lot of myths and wives' tales relative to whether or not they're going to do damage to a system by applying them. Can you address some of those and hopefully debunk some of that?
Well, I think we know a lot more about drives. We know a lot more about the wiring practices and the insulation systems and the motors, and all of those have been improved over the years. We know what kind of cabling to use. We know that better grounding practices are required with drives. And we just deal with it better today than we did in the past.
So the rumor that applying a variable speed drive to a motor is going to potentially blow it up, not true any longer?
Not with the motors we're building today. You'd have to really do some pretty bad things to it to blow it up. But there is still the case that if you took a drive and put it on an older motor, the insulation system in a very old motor is probably not going to handle the waveform of the drive. So a current NEMA premium motor is quite inverter friendly.
Ted, given that there's been some reluctance to adopt this technology up to this point, yeah, there's probably not a lot of experience in the field among end users in terms of how do they select a properly matched motor and drive. What advice can you give there?
Well, playing off of John's comments, I think that the industry practices have evolved. The desire to have these savings has built up considerable momentum. And so the manufacturers on the motor side have addressed the feature set to better handle the variable speed applications. And even the drive technology has evolved. So as the users are considering what they want to do, they should have some higher confidence that the equipment that's available is suitable. And in particular, that was one of the key points we talked about here. The NEMA premium motor is now designed. That's one of the benefits. It's inverter ready out of the box. So it's less likely that the end user is going to make an inappropriate choice. Even taking things as so far, I know Baldor markets marriage pre-selected motor drive packages and power matched performance. So there's been some convenience done to give people, hey, make your selections from these ratings, and you should have very high confidence that they're pre-engineered to satisfy those applications.
Okay. So as people are looking to to apply both NEMA premium motors and variable speed drives to some of these variable load applications, what are some of the considerations that they should take into account as they analyze the opportunity? Bruce, you want to jump on that one?
Well, to just touch again on what John said, in the past, a lot of original VFDs were like the size of closets and not necessarily well suited to the task they were put to. We've seen occasions where facility people have had VFDs on given applications in the past and have hauled them off because they were badly suited, low technology. The same technology now fits in a shoebox, creates a much smoother waveform for the motor. Again, the motor's better attuned to it. And the application of that, given size, lower cost, rebates and so forth, again, half of the applications that we see in the field are good candidates, be it compressed air, where you could reduce the load considerably, obviously with fans and pumping. There's no end to the applications, and really there should be, at this point, no fear with adopting this technology.
As the user's thinking about maybe a variety of different applications in their plant, those with the most restriction are the most attractive.
Mm-hmm. Restriction meaning mechanical restriction.
Yeah, that outlet damper on the air handler that's half closed is throwing away more than 3/4 of the energy it's consuming. So you can kind of hunt based on where are these devices, these mechanical flow controls, where are they set? Those with the greater restriction are the best to prioritize and go after first for upgrade.
And looking at it from a systems perspective, are there any other technologies that could be brought to bear, beyond the motor and the drive in a variable load application?
Well, we talked earlier in the previous segments about the power transmission drivetrain. The motor may go to a gearbox, may go to a belt drive. All of those have the potential to make a high efficiency selection. So we'd encourage optimize each of the components. You've got a solid foundation. And then it's dealing with the control and optimizing the process, getting the equipment to match the process demand, and remove any of the mechanical flow devices that really ties it all together, and it gives you the most leverage on the energy savings.
So again, I think what we're all saying here is that you have to look at it as a system. It isn't just the motor, it isn't just the drive, it isn't just the transmission. It's the system and how all those components interact to drive the process.
And to add to that, you can go into process control. You can create one drive as a leader and then have multiples of those as followers. So if you're mixing different things, you're pumping liquids into a batch, and you can ratio the different pumps to one another. No matter how fast you run the first motor, the others will proportionately keep up at the same ratios. So you're looking at process optimization. The compressor that Bruce talked about, you want to hold a certain PSI level in the plant. Once you pump the tank up, it's there. If you're not using any air, you can throttle the motor down, throttle the compressor down, just to maintain that pressure. As you start to draw air from the system, then the motor throttles back up to handle what the demand is.
So it's all adjusting automatically to satisfy the process. And so rather than fixed operations. You know, you have variable operations, but you've shaved and taken some of the inefficiencies out. You're more closely following that process, and it's all automatic.
Can you give an example as to how this has played out in the field with some of the customers you've worked with?
Yeah, and I think probably another indicator for people to listen for really is the belt part of this. Let's talk on fan systems especially. The belt is the common way to couple the motor and the load. And many end users will comment about, yeah, that unit over there, it's loud, it squeals. When you start it up, you can hear the slip. Well, that's another clue. So a customer we worked with had some supply and return fan equipment, and they had selected this to do their trial because of this indication. People said, that one is always a problem.
Right.
Even when we change the belt, even when we retension it, it just never seems right. It's always slipping, it's always squealing. So just the first step we took was to replace the V-belt with a synchronous product and go variable speed. And just that change, the savings was data logged before and after. That brought in excess of 20% energy savings to just deal with that slipping of the V-belt. And then the second piece was moving more to what John just illustrated, was to say, let's get this aligned to satisfy the process. And at that point, the system was reducing the speed and the volume by about 20%. That took the savings up over 65% energy reduction from the previous configuration. And it was kind of interesting because this occurred early summer, and in August we were back checking some things, tuning some things. It was 94 degrees outside. And although the system was following the temperature of the process it was serving, even with an outside temperature of 94 degrees, it hadn't needed to increase the speed above that 80% flow. So that was really useful for the customer to get the confidence that, hey, that system was oversized considerably. We kind of sized it down by the set point, and then optimizing the drivetrain, he saw phenomenal savings. And as a result, proceeded to upgrade another 40 units on the campus.
And two, what we call in our industry is NEVs, or non-energy benefits. Beyond just the energy, which we're all very focused on at the moment, the fact is, I'm sure in this case too, maintenance costs go down.
Oh, yeah.
Time on the wheel goes down. There's many other benefits to these moves besides just the energy savings.
Yeah, think of it as miles on the engine. Instead of running full speed all the time, you're at some reduced speed for a good portion of the time. You're taking miles off the engine, and that does pay a dividend on maintenance. Even the belt change was projected to give them a minimum 5 years of service before it would need to be tended to.
As opposed to?
So the maintenance benefits in there as well. And you're right, sometimes we lead with energy, and there's significant benefit that comes right along with that.
Sure.
But we look at that also under the soft start feature built into that. That's what you're talking about. You ramp the motor up to speed, and it is not going to have the mechanical wear on couplings and on what you're driving. It's not going to be like starting your car and revving the engine up and dropping the clutch on it, and boom, there you go. That's what happens when you start a motor across the line. The soft start does that for you.
Yeah.
Just as an additional benefit to a VFD.
Yeah.
And it keeps you from any peak demand charges you might get from a utility.